So today what I'd like to do is start reviewing for the exam by reviewing essentially what we've been doing for the last few weeks, interpolation, along with at the start here, Taylor's theorem, well, in particular, Taylor polynomials. I'll call it Taylor's theorem, but what we're really after is Taylor polynomials. And one new thing, and the basics of cubic splines, section 3.5. So that'll be one new thing that could be on the exam as well, but mostly we'll be reviewing because it'll be fairly time consuming to review everything. And let's consider this stuff in the context of a fairly simple example. F of x equals the square root of x. Let's use 4 nodes. X0 equals 0. X1 equals 1. X2 equals 4 and X3 equals 9. We're going to make the numbers nice here. So Y0 is f of X0 is square root of 0 is 0. Y1 is f of 1 is square root of 1 is 1. Y2 is f of 4 is square root of 4 is 2. And finally, Y3 is f of 9. Square root of 9 is 3. We'll use this to do everything that we've done in reviewing interpolation, except for Newton's forward and backwards difference formulas, because with those you need equally spaced nodes. But then if we have time, we'll also review Newton's forward, backward, and backwards difference formulas. And again, I also want to try cubic spline. So we're going to try all these approximation techniques and compare how they do effectively. Let's start with the technically simplest one, but least accurate overall, and that would be a Taylor polynomial. Taylor polynomial. It's not really interpolation in the main sense that we've been talking about doing interpolation. The general formula for P sub n of x would be the sum. Say k goes from 0 up to n of the nth derivative of the function evaluated at whatever point you're focused on. I'm not going to choose 0 here. That's the most common thing to choose. But 0 is a problem for a Taylor polynomial here because this function actually is not differentiable at 0. So I'm going to choose 1 instead. I'll put an a here to sort of represent an arbitrary number. Our book uses an x0, but I'm actually going to use x1 for our example here. Divide by n factorial and multiply times x minus a to the n power. Oops, k power, sorry. Not n. Replace all those n's with k's. So if you expand this out, when k is 0, 0 factorial is 1. The 0th derivative is the function itself. Raise something to the 0 power, you get 1. The first term is actually, the constant term is f of a. Then when k is 1, you get f prime of a divided by 1 factorial, which is just f prime of a times x minus a to the first power. Then when k is 2, you get f double prime of a divided by 2 factorial, x minus a quantity squared, etc., up to the nth derivative at a divided by n factorial times x minus a to the n power. We're going to use technology a lot today to save some time, but these are things you should be able to do by hand for examples like this. Let's start using Mathematica. I'll go ahead and type these nodes into Mathematica using the subscripts, except they're not going to be typed as subscripts. X0 is 0, X1 is 1, X2 is 4, X3 is 9. I'll go ahead and type Y0 is, I need to define the function. F of x is the square root of x. Y0 is going to be f of x0. Y1 is going to be f of x1. Y2 is going to be f of x2. And Y3 is going to be f of x3. So those are all entered. I'm also going to create a data list, you might say. of these points, x0 comma y0, x1 comma y1, x2 comma y2, and x3 comma y3. This will be convenient for making plots and also for using some built-in functions in Mathematica that I haven't shown you before, but will be convenient for checking our work. Anyway, there's our data. Again, I'm going to evaluate the Taylor polynomial to be centered at a equals 1. I'm going to use the a to be x1 is 1 again, because for this example, choosing 0 is problematic because the square root function is not differentiable at 0. And how big should n be? Well, it's up to me. Let's go ahead and say we go up to third degree. So we need f of 1, we need f prime of 1, we need f double prime of 1, and we need f triple prime of 1. So those are the coefficients that we got to divide by the corresponding factorials to get the third degree Taylor polynomial, which I'll call P3 of x. 1 plus 1/2 times x minus 1 minus 1/4 over 2 factorial, right? Which will be 1/8 because 2 factorial is 2. X minus 1 squared plus 3/8 over 3 factorial. 3 factorial 6. So that'll be 3/48, which reduces to 1/16. That should be the Taylor polynomial of degree 3 for the square root function centered at 1, a equals 1. You can check the answer with the built-in Mathematica function called series. Let's see if I recall the syntax. I think you put the function name first, then you make a comma and a list. I think you specify the variable name next and where it's centered and maybe the number of terms. Let's try that. Nope, that's not the right syntax. Okay, so I need to use the help menu and look up in the Wolfram Documentation Center series. I've got the wrong syntax, I guess. Look at an example. Oh, I probably need an f of x. Sometimes you just put the function name in. Sometimes you put f of x in. There we go. We don't need to go up to that 5th degree. Let's go up to the 3rd degree. Check this over. Compare it with this. Yes, it looks right. What is that saying there? That's just saying the infinite series has higher order terms, 4th degree and higher. That is not a 0 there. That's a big O. Big O of x minus 1 to the 4th means all the other terms are x minus 1 to the 4th power and higher degree. So we have a match. How well does it do in approximating the function? Let's plot them both f of x and P3 of x. Over what kind of interval? Well, let's try 0 to 2 and see how it goes. Let's make the original function blue and the approximation red. There we have it. So the square root function is in blue, and this cubic function is in red. And you can see over the interval from 0 to 2, generally speaking, it does pretty well from about 0.5 to 1.5, within half a unit of 1. We could use the theorem and the error bound to more precisely say what the error is. Not so well when you get close to 0. You can see the absolute error is in the ballpark of a 0.3 or so there. If you go to a bigger interval, like say -2 to 4, well, it's a problem. For one thing, the square root function is not defined when x is negative. If you're talking, you want real outputs at least. And even when x is positive, but bigger than 2, the approximation starts to get bad and can get really bad. Say we go up to 10 or something like that. So the approximation is doing well near 1, in particular between 0.5 and 1.5. What would the error bound theorem say in this context? It would say the absolute error, absolute value of the actual function output with the approximation is less than or equal to, what was it? It was the absolute value. Well, okay. Let's say it's m divided by 4 factorial. You have to increase the n by 1. Remember dividing by n plus 1 factorial. Times the absolute value of x minus a to the 4th power, where m is an upper bound on the absolute value of the 4th derivative of the function over the interval. This is over the interval in question. Interval in question. What's the 4th derivative of f here? It's that. How big does that get on the interval from 0.5 to 1.5 in absolute value? I can get rid of that negative sign. Looks like the biggest it gets is at 0.5, and we could even plug in its value at 0.5. Replace x here with 0.5. About 10.6 is the biggest that the 4th derivative will be on the interval from 0.5 to 1.5. So you could take about 10.6 or 10.7 if you want to play it safe for the m. If you divide that by 24 factorial, which is 24, you get something less than a half. And if you multiply by this, which will be less than 0.5 to the 4th power, right? If we're on the interval between 0.5 and 1.5, this will be less than 0.5 to the 4th power. That's a half to the 4th power, which is 1/16. So we're talking an error less than or equal to 1/2 times 1/16 or so, 1/32 on the interval between 0.5 and 1.5. Let's go back to that interval here. 1/32 is about 0.03 or so. These graphs never get further than 0.03 apart on this interval. Okay, does it feel good to review this? Remind yourself of some things. Okay, now let's do interpolation. Let's use, so this is the Taylor series approach. Taylor polynomial, I'll call it. Let's label this Taylor polynomial. Now let's move on to interpolating polynomial. Big picture wise, what did we do in chapter 3 so far? We started with a Lagrange interpolation, which essentially we used a formula involving, well, it's a complicated formula involving tricky polynomial constructions to come up with a polynomial approximation to the function using a certain number of nodes. Next thing we did was Neville's method. In Neville's method, you're using Lagrange interpolating polynomials of various degrees, each column corresponding to first a 0th degree, then 1st degree, then 2nd degree, to ultimately get a highest degree polynomial approximation, a single one, at a numerical value. The focus is more on numerical values, plugging in particular numbers. We have a table, we can make a spreadsheet. Next thing we did was divided differences, thinking about what's technically called the Newton form of the polynomial expansion, which I will show you can actually compute in Mathematica pretty quickly. And first solving for the coefficients as divided differences and making a divided difference table. And then showing that you can also do that with the forward and backwards difference formulas involving binomial coefficients and also forward and backwards difference operators instead, if you prefer, as long as the nodes are equally spaced. And then we did the Hermite interpolation, where we're trying to match up the derivative values as well. And the easiest thing to do in the end is to once again make a divided difference table. So you have to make some modifications. That's big picture what we've done so far. If you want to get Mathematica, if you've got Mathematica available and you want the interpolating polynomial available as fast as possible, there's a built-in formula. Interpolating, I can spell, polynomial. How about that? Look up some information about it with the syntax here. If you've got data, it looks like this is data here. Some x values and some f values, some function outputs. Those f's would be y's. If we want an interpolating polynomial in x with those data values, which is what we've got, that's the syntax. It's not too bad. And in fact, we already have the list data entered as the list, kind of list that we want. Where is it? Right up here. So I can just use that thing that I've saved in the variable name data. I probably can just do this. Hey, it looks like it's expanded, doesn't it? In that funny way. How would we write this by hand? So now I'm using all 4 nodes. Using a piece of paper. X0 again is 0, X1 is 1, X2 is 4, and X3 is 9. And I am evidently what Mathematica is saying here is that what would the degree be? The degree would be 3. It would be a cubic. The degree 3 cubic polynomial that interpolates these points exactly can be written like this nested form. And if you partially expand this out by first distributing the x through here and here, what would that become? And also distributing the x minus 1 through here and here, what would we get if we do that? Let's see, we got to have a 1 times x is just x. The constant term is 0, by the way. Let me go ahead and write the constant term, 0. I could call this P3 of x as well here, but it's a different P3 of x than the Taylor polynomial. It's going to be a degree 3 interpolating polynomial. The fact that 0, 0 is on the graph is why that first term is 0. Actually, the fact that the first output at the 0th node is 0. The 0th node being 0 itself doesn't really matter. It's the fact that y0, the output at the 0th node is 0, is why we get a 0 there. Plus 1 times x, just x. What would be the second degree term? It would be x times x minus 1 times negative 1/6. And then the third degree term, the coefficient is going to be 1/60th. And the factors will be x times x minus 1 times x minus 4. This is a Newton expansion, you might say. And these coefficients, including a 1 right here, are divided differences. The 0 is f of x0. It is f of 0. The 1 is the divided difference f of x0 comma x1. The negative 1/6 is the divided difference f of x0 comma x1 comma x2. And the 1/60th is the, let's see, that's a 0th, first, second. This will be a third divided difference, f of x0, x1, x2, x3. Let's confirm this with a spreadsheet. let's go ahead and make a divided difference table to confirm that these really are the same things as you get with the divided difference table. Along the upper left to middle right diagonal. Not Neville's method, this divided differences here. So let's see. Let's make a column for I. Let's make a column for xi. And the f of x I here. That's a 0th divided difference. 0th dd. First dd, second dd, and third dd. 0, 1, 2, 3 are the subscripts. Okay, so divided difference table, so I need to make spaces, sorry. It's not Neville's method. The x's themselves are 0, 1, 4, and 9. The 0th divided differences are function values, so just take the square roots of those things. Nice numbers. Yes, this 0 corresponds to the 0 right there. For this one, we got to do an actual divided difference. Like this, remember it? First divided difference. We'll copy and paste that down. This is obviously going to do 1 minus 0 divided by 1 minus 0 is 1. Matching the 1 right there. Are the other first divided differences relevant? Well, they're all 1s, just by chance in this case. In general, they don't have to be the same. They don't show up as the coefficients, but they are necessary to compute other coefficients as we continue the table. Second divided difference. Supposed to get 1/6 here, right? But we're not. What's going to happen? Why is that happening here? Yeah, I used I instead of xi, sorry. Gets the right answers in this one. No, it doesn't get the right answers in this one. Okay. Let's do over. Dangers of putting I in the table. There we go. That's better. Okay. Second divided differences. Yeah, this next one should be negative 1/6. It's going to be negative 2/3 divided by 2. That will be negative 1/6. Thank you. Maybe as a general rule, don't put I in the table. So negative 2/3 divided by 4. Yeah, that is negative 1/6, negative 0.16 repeating. Copy and paste that. I'm not going to use the I column this time. I'm thinking about it. There's our third divided difference. That's going to be the 1/60th. So what is that? 0.016 repeating? Yeah. So yeah, the numbers 0, 1, negative 1/6, and 1/60th, they match these coefficients. There, and there. These are we originally called these A's. We called this A0, then A1, then A2, then A3 in the Newton expansion. Are they the same coefficients you'd get if you expand this out? None of them are except for the 0th coefficient being 0. That's the standard form of the polynomial. All right, let's plot it. Compare it with f, see how it does. I'll just, I could call this P3. I'll just copy and paste it right here. See how it does on the entire interval from 0 to 2. Or 0 to, we should go 0 to 9, shouldn't we? Does it do pretty well in the entire interval from 0 to 9? Let's see. Not so well. It's kind of a big interval, though. That's why. For such a big interval where these nodes are so far apart, we want a higher degree of polynomial. We'd want more nodes. Just trying to illustrate ideas here. But it does go through the right points, 0, 0, 1, 1, 4, 2, and 3, 9. I could add those to the plot by doing a list plot of the data. There they are. I can type that fast because I've typed it so often. I've used Mathematica a lot in my life. Well, just for fun, let's have Mathematica. How about we do this? Let's have Mathematica compute a big list table of data with lots of nodes. Oh, this could be fun. How many nodes should we use? 23. 23? Your wish is my command. Let's see. I is going to go from 0 to 22 to make 23 nodes, but I don't want to do f of I there. I guess, let's see. What do I want to do? I times 9, what would it be? The interval is length 920 seconds. Is that going to do it right? Yeah, I guess that'll do it right. And that will include 9 at the very last one. Except I don't want the first thing to actually be an I. I want to divide I by, multiply that by 920 seconds as well. Yeah, that's going to give us 23 nodes. N is 22. And oh boy, you ready for this one? Interpolating polynomial. I am so excited to see what this does here. More data, X. Woo! Can I call that P3 of X? Will this work? I'm not sure. I guess so. Hey, let's expand it. There it is, 22nd degree polynomial. How does it do? I guess it's not P3 anymore, is it? I shouldn't call it P3. P22. It's 23 nodes, but the degree is 22. There we go. I can't tell the difference between them except near 0. Woohoo! It's more than just those 4 data points too. Oh, okay, more data. There we go. All right. In general, if you don't have a well-behaved function, here's a comment, an important comment. In general, if you don't have a well-behaved underlying function, like a well-known function like the sine function or a square root or a logarithm or something like that, and it's possible your function could be ill-behaved, oscillating rapidly, you don't typically want to use a high degree polynomial for interpolation in that kind of situation, unless it was really high degree. But then it would be bad to extrapolate, and it's bad to extrapolate here as well. Watch this. If I plot this over a bigger interval here, oh, maybe even -3 to 12. I'm sure it does badly once you get past the interval from 0 to 9. How about that? Extrapolation's not doing so well. It's the interpolation that's better. Even -1 to 10. Okay, isn't that cool? Okay, that's kind of fun, huh? I don't want to make a spreadsheet divided difference table for that one, though. No. Okay, what else is worth reviewing here? It's probably worth reviewing Neville's method. So back to the spreadsheet. But we need to construct our table differently. By the way, if I was going to use this within the spreadsheet to approximate the square root at some value of x, let's quickly do that. Let's say x is 3. The exact, so to speak, well, that's not really exact, but best approximation in the spreadsheet is given by that 1.73205081. Approximation. We'd have to do this, remember, plus this times x. In general, it's x minus x0, but x0, 0. Plus, so maybe I should emphasize that by doing this. Like that. In general, x0 is not going to be 0. Plus this times x minus x0 times x minus x1 plus that times x minus x0 times, oh, come on. X minus x1. Sorry, you can't see it so well. Oh, come on. Ah. E3 minus B9, I meant to do. Sorry, it's hard to see now. E3 minus B11 is the last thing I'm typing. You don't have to do E3 minus B13, right? You don't have to do X minus XN. It's already taken care of in the interpolation. It's kind of nice. Not so good. The error is bigger than we usually like. It's not surprising that third degree didn't do so well visually either. Yeah, let's now review Neville's method. It is good with Neville's method to also have a column for x minus xi, just as a convenience. Once again, x is 3. We have the funny notation with the p's and the q's. That is probably worth reviewing. But first, let's plug in the i's and the xi's. X minus xi. Let's go ahead and use a fixed cell reference. E15 minus that. Using dollar signs, technically called an absolute cell reference. Copy and paste that down. All right, what was the notation again? This is, again, perhaps the hardest part is the notation. Let's see if I can remember it correctly. Let's see here, the P's, the I did refer, there's 2 subscripts. The I did refer to the, no, there's more than 2 subscripts. It was the Q's that have 2 subscripts. T sub I. This is going to be the 0th degree column using 0 degree polynomials, constant functions, to approximate the underlying function at the nodes individually. It's going to be 4 of them. So you really just use the function values, or the numbers that go in there. The 3, the 0, 1, 4, and 9. Yeah, it is just PI. And when you only have 1 subscript on the P, that means it's a 0th degree. Q, the first subscript corresponds to the row, 0th row, first row, second row, third row. The second subscript corresponds to the column, like a matrix notation. There you only always have two subscripts. Do you have to use that notation? No, you don't have to. It's just, these are both convenient and they both do have a logic to them. Again, you're just using function values, which I guess I don't have in here yet, but I can just do SQRT, or I could just type them in since the numbers are so nice. They'll be 0, 1, 2, and 3. Same as the xi's by chance. So those you want to think of conceptually, if you watch my extra video, as being 0th degree polynomial approximations, constant function approximations to the underlying square root function, which is increasing and concave down. Not very good approximations, but conceptually, that's what you want to think of. Then we have the first degree approximations. And how do we want to do the subscripts here? We want to, with the first degree, we're doing 3 of them using 2 nodes at a time. 0 and first node, first and second, second and third. By convention, we're starting in the second row, which is really the first row. The first row is really the 0th row. Not that we have to, it's just a convention. We could have started here. You got to pick one of these 2 as the spot you put your answer in. So if we're putting it in this spot where I is 1, that's the row where I is 1. We want to use the 0th node and the first node. So the subscripts on the P should be I minus 1 and I. Because we're going to use the 0th node and the first node in this row that is called the first row. That's supposed to be a lowercase I. It made it uppercase. And the Q is going to be I and 1. Ith row, 0, 1, 2, and 3. First column, which is really the second column. Might be nice if we make these actual subscripts. Format. Subscripts. Oh, it didn't work. I don't know why it didn't work. Try it one more time. I don't know why that didn't work. Format, cells, subscript. Didn't I click subscript? I don't know what's going on. Okay. Start here. And then it was tricky. Start in the upper left. X minus x0. Oops, use parentheses too. X minus x0. I'm already doing subtraction there, so I don't have to actually do a subtraction on the formula. Times this, but now you do a subtraction because you're going to subtract something else, another product. Times minus this times that, all divided by x1 minus x0. Take a look at that. Take a second to look over that. You go diagonally, upper left to lower right first, then minus, the typo in the book was they put a plus there. The product lower left to upper right. That difference gets divided by x1 minus x0 here. And what this is really doing is this is using a straight line to approximate the function between the 0th node and the first node. Without actually computing, we should be able to guess what the answer is. The function outputs we know are 0 and 1. We're using a straight line to interpolate, actually extrapolate past there to x equals 3. Should we get 3 here? Yes, we do. See what I'm doing visually? I'm not doing it on paper. Maybe I should do it on paper. I didn't do it before. What we're doing, what we just typed was essentially taking these two data points, 0, 0, and 1, 1, construct the interpolating polynomial for those two data points, two nodes, 0 and 1, which is a line with a slope of 1 to the origin. And we are going out to 3 and using that line to approximate the square root function at 3 to be 3. Of course, the underlying square root function doesn't go that high. The underlying square root function is more like this. But that's what we're doing. And using the formula in that way. It's a weighted average, effectively, where I don't want to go into details. The weight for the 1 is much more than the weight for the 0 because 3 is to the right of 1. In the conceptual video, the extra video, I go into thinking about that as a weighted average. We don't have time. I would, if you never watched that, I would recommend watching it. I really gave my best effort in it, and I think it really is helpful conceptually for understanding what Neville's method is about. But at the moment, we can just copy and paste this formula down here and here. 1.6 repeating. These are all approximations to square root of 3. Let's draw more pictures here. The second one, the 1.6 repeating, is taking the nodes at 1 and 4, where the output is 2, and using a straight line connecting those 2 points to approximate the function value at 3. And the second coordinate of this point right here should be 1.6 repeating. On this green line here. The true square root of 3 is a bit higher, 1.7, I believe. That's what we just did in getting this one. I'm going to run out of battery. This thing, somebody turn this off. There we go. And then the 1.8 is using the second and third nodes, 4 and 9, and the straight line connecting them and going back to x equals 3. And that's why you get something a bit higher, 1.8. That's what's going on behind the scenes, conceptually speaking. The next column is a second degree column. We're going to use quadratics. But for quadratics, you need 3 nodes. P, we're going to start in this spot where I is 2. So notationally, we need P sub I minus 2, comma, I minus 1, comma, I equals Q sub I, comma, 2. And this is the place where it's easiest to make a mistake. Am I going to make a mistake? I think I remember it right. You once again go x minus xi times a previous column's p-value. But you have to always start with the x minus xi in the I equals 0 row. That gets multiplied by this. And you subtract, but then when you do the other multiplication, you do not go up to here because there's a blank up there for one thing. That's one way to realize don't go up there is there's a blank up there. Do this times this. And then you divide by xi minus x0. I almost did 2 minus 0. Again, it's dangerous to have the I column in there. If you don't put it out, if I have a take-home portion and you do something in the spreadsheet, you don't have to have the I column in there if you're afraid it's going to mess you up. This, once again, should be an approximation to the square root of 3, a quadratic approximation, and it should be not too bad. Okay, it's not as good as I was guessing. Remember the true square root of 3 in the spread up to spreadsheet approximation is that. Finally, we do a third degree approximation. P sub I minus 3, comma, I minus 2, comma, I minus 1, comma, I equals Q sub I, comma, 3. Go to that column again, times this, minus this, times this, all over this minus this. So this hopefully shouldn't be too far off from 1.732. Did I make a mistake? Or maybe it's just a bad approximation again because our nodes are far apart. What did we get before? Yeah, we got 1.9 before. It's correct. Not a great approximation. Okay, if we use more nodes, better nodes closer to 3, we get a better approximation. Time is flying by here, for me at least. 15 minutes left. I do want to talk about splines. So let's spend the last 15 minutes talking about splines. So I'm skipping for today because we didn't have time, divided differences in the full generality and also Newton's forward and backwards difference formula. Don't forget about the discrete calculus too. Those kinds of basic things could be on the test as well. But let's spend 15 minutes talking about cubic splines. How far can we get in 15 minutes? Cubic splines. And do I want to use 4 nodes? Let's see how far we can get. Yeah, let's use the 4 nodes, 0, 1, 4, and 9 again. X0 is 0, X1 is 1, X2 is 4, X3 is 9. Once again, Y0 is 0, Y1 is 1, Y2 is 2, Y3 is 3. With a cubic spline where you've got 4 nodes like this, n is 3, it's a piecewise function. It's piecewise cubic. And if you've got 4 nodes, there are 3 subintervals, so to speak. They're going to be 3 pieces. That are all cubics. We're splicing together a bunch of cubics, thus the name spline. Spliced lines, and they're cubic functions. Splines, that's a word. Cubic splines. Not sure if I'm going to get consistent with book notation here. Forgot about Hermites too. We got Hermites to review next Monday too. Okay, yeah, this is consistent. We'd have A0 times, just as a constant, plus B0 times X minus X0. Now X0 is 0, so that's just X. Plus C0 times X minus X0 squared. Once again, X0 is 0, so that's just X squared. Plus D0 times X minus X0 cubed. Again, X0 is 0, so that's just X cubed. This is going to be the form of the formula over the first interval. Over the second interval from 1 to 4, we'll use the same letters A, B, and C, but different subscripts. A1 plus B1 times X minus X1. X1 is not 0. So write it like this. Then C1 times X minus X1 squared. Then D1 times X minus X1 cubed. And this is valid over the second interval, which goes from the first node to the second node. And I guess I'll write the inequalities like this. I picked a less than or equal to there and a less than there, but I could have switched those around. We're going to want these pieces of this function to match up in a continuous way. And then the third piece, use the second node for and write it like this. Three cubics that I'm piecing together, splicing together, thus the name spline. I guess you could think of it as like splints as well, either for bones or a tree or something that are being spliced together. How do you splice these together? You splice them together in a natural way. You want the function values at the nodes 1, 4, and where these match up, 1 and 4 to match. You want the function values. You want them to match up in a nice way. You want the derivative values to match up. And to be even more nice, you want the second derivative values to match up. We have 12 unknowns here that we have to solve for. Thanks. We're going to need 12 equations ultimately. Making these match up at those nodes doesn't quite give us 12 equations. Let's see how many it gives us. So let's use Mathematica now. This could be something I could have you use Mathematica for. We will give names to these pieces. I'll call this S sub 0 of X. Call this S sub 1 of X. And call this S sub 2 of X. And a nice way to do this, the nicest way I can think of to do this in Mathematica is as follows. I'm going to use the subscript button. Type S0 sub A0 underscore B0, comma B0 underscore, comma C0 underscore, comma D0 underscore, tab over of X underscore colon equals A0 plus B0 X times X plus C0 times X squared plus D0 times X cubed. There's my first piece. Save some time by copying and pasting, change the zeros to ones. There, change these zeros to ones as well. And then change the x's to various powers to x minus ones. One more, copy and paste this. Change the ones to twos. All the ones get changed to twos. Including inside the parentheses here. Enter all that. Fun, fun, fun. Okay, so Mathematica solve a list of 12 linear equations and 12 unknowns for these 12 unknowns. Thank you for that. Would have been a bad mistake. Thank you so much. But I'm going to keep the other things too. Twelve unknowns. What are the 12 equations? Again, you want the function values to match up. So, for example, you want S0 of A0, B0, C0. Remember, after you use the underscores, you don't need them anymore. At the first node, which is 1, I guess I could type an X0 in there because I've already entered that. Maybe I should. To equal S1 at that same node. Oh, not, excuse me, the first node, not the 0th node. That's where these pieces are matching up. That's one equation. You also want their derivatives to match up there. I think you got to put the prime here. And their second derivatives to match there. Make sure when you type the prime, that's not down in the subscript.
Down in the subscript, yes.
Thank you. That's at, so there's the 0th node, the first node, the second node, the third node. That's at the first node. We're focused here at the first and second nodes that are in the middle, not the endpoints. Because these are where the pieces of the function need to match up. So far, that's giving us 3 equations. If we match them up also at the second node by changing the x1s to x2s, now we've got 6 equations. We need 12 equations. What else do we want to happen? I'm remembering some of them, but forgetting some, I think. Well, it depends on what you want, really. You do want these to also equal function values, the underlying function. So you also want S0 of x1, for example, to equal f of x1. You also want S1 of x1 to equal f of x1, but if S1 of x1 equals S0 of x1, it'll automatically equal f of x1. Solving a bunch of equations simultaneously here. We want S1 to equal f of x2. And S2 to equal f of x3. Okay, depends on what you want. We do want them to equal all the nodes. So including the 0th node and the third node. So I'm going to put S0 of x0 and f of x0 in here as well. And if I go to the third node, I need to use S2 at x3. I'm probably going to get crazy fractions here, right? For the answers. How many equations do we have now? 9? 10? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need 2 more. What are they? There are 2 options. One is called the natural boundary option, and one is called the clamped boundary option. The natural one generally is thought of as better, though it's not necessarily the best. And what is the natural one? You want the second derivatives at the far endpoints to be 0. Makes the graph close to straight at the endpoints, which for relatively well-behaved functions is typical. So we want the second derivatives not to equal function values or derivative values, but 0 at the left endpoint and the right endpoint, which we'll need S2 for. And the right endpoint is x3. If I've fixed all my typing mistakes, hopefully this will be good. Empty set. No solution. Okay. I'm not sure what's wrong. Do I really have 12 equations? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Is it possible that the system is just inconsistent? I don't think so. I'm not sure what's wrong. Almost out of time. The clamped boundary condition would match up the derivatives at the endpoints with the derivative of the original function at the endpoints, which is problematic for the square root function, though, because remember the square root of x has an infinite slope at 0. The derivative is undefined at 0. So you would not want to do a clamped boundary condition where you specify the derivatives at the endpoints. I mean, we could do that here, but it's not going to match the square root function. I mean, f prime of 9 could be matched up. 1/6, I could do that. But the derivative of the square root function at 0 is undefined. F prime of 0 is undefined, complex infinity. So it'd be problematic here. I mean, I could pick a big number like 10 or something, see if it gives an answer, but it's not giving an answer. So I'm not quite sure what the problem is. Easy to make a mistake in such a short time. I will try to fix the mistake here after class. I'm hoping there's a mistake that's fixable. What's more important is you understand the idea of what we're trying to do. We're trying to piece together 3 cubic functions to match up. And you would then define the function finally. Let me just do this real quick. You would define the final function as a piecewise function, which can be done in Mathematica, either with a built-in command which or this button over here, this piecewise defined function button, which you can add a row to by doing control return. And you would do this kind of thing and specify the domains for each. And I'll do that as well. Hopefully fixing my mistakes. Okay, have a good day.